In this video, I'm going to discuss how the attention layer of LLMs work and how we can interpret them through the lens of the query key value database analogy. First, let's cover matrix multiplication. So for two matrices to be multiplied, they have to have compatible dimensions. Here, a 2x3 matrix is multiplied by a 3x2 matrix. The dimensionality of the output matrix will have the first dimension from the first matrix and the second dimension from the second matrix. To get the value for the first row and the second column of the output matrix, you would do pairwise multiplications across the first row of the first matrix and down the second column of the second matrix, and then you would sum those up. So C12 would equal A11 times B12 plus A12 times B22, and so forth. That's why the matrices have to have compatible dimensions to be added. The last dimension from the first matrix has to equal the first dimension from the second matrix. So why are we talking about matrix multiplication? Well, it's because they're fundamental to how LLMs work. The secret sauce of the transformer LLM architecture is the attention layer. And the attention layer takes in an input X, which will have dimensions S by M, which is the length of the input sequence and the model's dimensionality. So higher dimension models are able to encode richer information about the semantics of each input element. But before the attention layer runs, these vectors of length M just contain information about each token in isolation, not with information that includes how it relates to the rest of the input. So for example, consider the input sequence. The ball was small, white, and dimpled. Before the self-attention layer, the element for ball would represent the semantics for any kind of generic ball, not specifically a golf ball, like you would know if you read the rest of the entire sequence. But the attention layer passes this input to several matrices of coefficients that it was trained to learn, and it does matrix multiplication with them. One of those matrices produces a value Q of size sequence length by an internal value K. Now, like model dimensionality, the model architects choose what this K value will be. But we can think of this matrix as producing a database query, and we're going to call that Q. Another one of these matrices produces a value K of the same dimensionality as Q. We can think of this as being the primary keys of the database that we're going to query with Q. A third matrix produces a value V of size sequence length by V. And for self-attention, this V value would equal the model's dimensionality. So V would have the same dimensions as X, which is S by M. But we can think of V as being the fields in our database that we're going to query using the primary keys. The attention layer transposes K so that its dimensions are now K by S. So now it's compatible with Q, and those two can be multiplied to create a matrix of size S by S. This then goes through a softmax function, which normalizes the values in the matrix so they sum up to 1. These are the attention scores that, for each element of the input sequence, tell the model what other parts of the sequence are relevant to it. So this is like executing the database query against the primary keys of our database, and now finding which rows of the database table are relevant to our query. So finally, the attention layer will multiply these attention scores with V to produce an output dimension of sequence length by the model's dimensionality. So this is like getting the actual values from the rows in the database based off of the primary keys that we found before. The attention layer produces context vectors for each token to give the model information about how it relates to the rest of the input. Before, those context vectors only contained information about each token in isolation. But after running this attention layer, the context vectors contain information about the token after taking into consideration the entire input sequence. So now, again, consider the example that we had before. The ball was small, white, and dimpled. Before the self-attention layer, the element for the ball would represent the semantics for any kind of generic ball. But after running the self-attention layer, the element for ball also incorporates the information about the ball being small, white, and dimpled. So now that vector has been updated, and it should be semantically closer to the vector representation of golf ball. Now for inference, the LLM would use these context vectors in a subsequent layer to predict the next best token. The final token's context vector will contain information about the entire input sequence, and it can effectively function as an embedding. Now, this was for self-attention, and for multi-head attention, the attention layer identifies distinct ways in which elements of the input sequence relate to each other. So for example, you might have one head that is specifically functioning to identify the subject associated with the verb. So if you had a sequence, John threw a ball, a head that functions as a subject identifier would highlight that John is the relevant element for the element threw. The difference compared to a single head attention is that V no longer equals the model's dimensionality. It's decided by the model's architects, and here each head would produce the intermediate attention outputs that we discussed previously, and they would produce outputs of size sequence length by V. So the model architects decides how many of these attention heads there are, but before the output is produced, each of these matrices are concatenated with each other, and they produce a single output of size sequence length by M. So M is equal to V times N, where you have N attention heads. So that's how attention works at a high level. You have three different matrices of coefficients. One of them produces a value Q, which is like a database query. One of them produces a value K, which is like the set of primary keys that your query will run against. And Q and K are combined to produce a set of attention scores. Those attention scores are like the set of primary keys in the database that you're interested in. V is like the actual values in the database that are associated with each primary key. So when you multiply V by the attention scores, you then get an updated context vector for each element of the input sequence that better identifies how it relates to the rest of the sequence. And if you're using multi-head attention, then you can have those context vectors identify multiple distinct ways that each element relates to one another.